Hi everyone. So today we are going to be covering chapter or section 10.6, which covers alternating series. Now, alternating series are a specific type of series. I will go into in particular what they are. But the really nice thing about alternating series is that they are much easier to deal with than regular series. So regular series, right, we need all of these different tests for telling if something converges or diverges. You need to consider if it's easy to take integrals. You might need to know what to compare your series to, all of these things. In the world of alternating series, however, it is much easier to determine whether they converge or whether they diverge. Okay, so what is an alternating series? So an alternating series is a series k equals 1 to infinity, negative 1 to the k plus 1 of a k. Okay, so where these AKs are positive. Basically, what this means is that we are bouncing back and forth between positive and negative numbers. Right? Whenever k is odd, k plus 1 is even, and so we have a positive term. And then when k plus 1 is odd, so k is even, we have a negative term. So every time we start by adding something and then subtracting something and then adding something and then subtracting something, and so on and so forth. The really nice thing about alternating series, however, as I mentioned before, is that it's much easier to tell whether they converge or diverge. So in particular, we actually have that the opposite direction or the converse of the divergence test is going to be true in this case, with one extra condition that we need on it. But, so in particular, what I mean is if my terms are decreasing, so k plus 1 less than or equal to ak, or so non-increasing, right? Remember, these AKs are the positive part of my series, and then it's going to bounce back and forth between adding and subtracting this positive part. And my limit as k goes to infinity of AK equals 0, then my series converges. Oh, that should be AK converges. Right, so this is basically the opposite of the divergence test, where we now have this limit of the terms going to 0, and we get now that the series converges. So the divergence test for specifically alternating series will also tell us convergence. Now, we also need this additional factor that my terms are going to be decreasing, or specifically non-increasing, which in most of the cases we've dealt with makes sense, right? So for example, 1 over k squared, any of the p series, in those cases, right, we have non-increasing terms. So all of these cases, we do have non-increasing terms. So this is not a super strong condition, but it is something that we need to actually check in order to use this alternating series test. This is the alternating series test. Okay, so let's look at some examples. Example 1. Let's go back to our old friend, the harmonic series. K equals 1 to infinity, negative 1 to the k plus 1 over k. Right, we've talked about this a lot. This is a p series, right, with a p of 1. If this negative 1 to the k plus 1 wasn't there, this would diverge, right? Because we have a p as 1, and we know from our p series test that means it's going to diverge. However, what about the alternating harmonic series? That's what this is called. Alternating harmonic series. Okay, well, we need to check two things. We need to make sure our terms are non-increasing to use our alternating series test, and then we need to show that the limit of the terms is going to be 0. So we have 1 over k plus 1, and we'd like to show this is less than or equal to 1 over k. As we've talked about previously, right, when we take reciprocals, we flip the sign. So this is the same as showing that k plus 1 is greater than or equal to k, which is certainly true. So we do have this condition where the terms are non-increasing, and again, 1 over k is always positive, and so we do satisfy this first condition here. Now the second condition is we would like to show that the terms go to 0, so the limit as k goes to infinity of 1 over k. Well, oh, that was a terrible k. 1 over k. We are doing 1 over a number that's getting bigger and bigger and bigger, and so surely this does go to 0 in this case. So by the alternating series test, this series here, k equals 1 to infinity of k is going to converge. Yeah. So this is really interesting, right? We took something that we knew diverges. We made it an alternating series, right, where we're bouncing back and forth between adding and subtracting terms now instead of just adding them. And we now get that this series is going to converge instead of diverge. So another example is going to be sum from k equals 1 to infinity of negative 1 to the k plus 1 over k squared. Okay, so this one converges without this negative 1 to the k plus 1. So what about the series itself, the alternating series? Is this going to converge or is this going to diverge? So we need to show a couple of things. We want to show that our terms are non-increasing. So again, we know that k plus 1 squared is certainly bigger than k squared. Taking reciprocals, we get that 1 over k squared, k plus 1 squared over k plus 1 squared is less than 1 over k squared. And so we do know that my terms are going to be non-increasing, right? And this makes sense. As I put in larger and larger k values, I'm going to get larger and larger numbers on the denominator, and this means that my entire fraction is going to get smaller and smaller and smaller. Okay, so we've satisfied the first condition with these AKs as 1 over k squared. And then similarly, limit as k goes to infinity of 1 over k squared is going to be equal to 0 still, right? We're getting 1 over a huge number, so this is going to be 0. So by the alternating series test, k equals 1 to infinity, negative 1 to the k plus 1 over k squared is going to converge still. An important thing to note is that if this limit as k goes to infinity is not equal to 0, so for example it's equal to 1 or 2 or infinity or anything like that, or does not exist, then my series is going to converge, or sorry, is going to diverge, no matter what. And we can prove this using our divergence test as well. So the opposite of the alternating series test is still going to hold. Okay, so these two series kind of lead us into an idea that we're going to call converges absolutely and converges conditionally. So we say that some series k equals 1 to infinity of ak converges absolutely if we take some absolute values and it still converges. Okay, and we say it converges conditionally. If just the series itself converges. So in the case where all of my terms are positive, converges absolutely and converges conditionally are the same thing, because taking these absolute values isn't going to change anything. This is more interesting, however, in the case of alternating series or just series where we can have negative terms, right? So we're not just adding things, but we might also be subtracting things. So from the examples above, right, we have sum from k equals 1 to infinity, -1 to the k plus 1 over k. Well, if we take absolute values here, we would get 1 over k. And we know this is going to diverge from our p-series test. It's the harmonic series. It's always going to diverge. So it doesn't converge absolutely. However, we know this series does converge, and so it converges conditionally. However, taking this series here, k equals 1 to infinity, -1 to the k plus 1 over k squared. Well, now if we take absolute values of this, we have our 1 over k squared here. Using a p-value of 2, we know from our p-series test that this is going to converge, and so this converges absolutely and conditionally. Right, because both when we take absolute values and when we don't take absolute values, it's going to converge. So in general, if a series does converge absolutely, it is going to converge conditionally. It converges absolutely. It converges conditionally. So basic idea behind this is subtracting terms only makes it more likely for something to converge, just converge in general, right? So if we subtract things, makes it more likely, and so if it does converge absolutely, then it's going to converge conditionally as well. Okay. So let's go through a few more examples of things that converge absolutely, converge conditionally, or maybe diverge. And we'll just be dealing with 3 more alternating series in this. So example 3. We are looking at the sum from k equals 1 to infinity, -1 to the k plus 1 over the square root of k. Okay, well, we have this idea where if the series converges absolutely, it converges conditionally. So let's start by checking if this is going to converge absolutely, because that's going to give us both, right? It will give us both absolute and conditional convergence. So the absolute value of this is the series from k equals 1 to infinity of 1 over the square root of k, or k to the 1/2. Well, this is a p-series with a p as 1/2 as our exponent. And if we remember back to our p-series test, this is going to diverge. Okay, so it doesn't converge absolutely. What about converging conditionally? So doesn't converge absolutely. Absolutely. So what about conditionally? Well, we need to check a couple of things for this. We're going to use our alternating series test because this is an alternating series. So we certainly have that k plus 1 is greater than the square root of k. So taking reciprocals, we have 1 over the square root of k plus 1 is less than 1 over the square root of k. And so we do meet our condition where the terms are going to be non-increasing. The second thing we'd like to show that this is going to converge conditionally, is we'd like to show that the AKs, or this square root of k, 1 over the square root of k, is going to go to 0. So the limit as k goes to infinity of 1 over the square root of k. Well, what happens in this case, right, we have 1 over a big number, so this is going to be 0. And so by the alternating series test, k equals 1 to infinity, negative 1 to the k plus 1 over the square root of k converges conditionally. So like the alternating harmonic series, this is an example of something that doesn't converge absolutely, but does converge conditionally. Okay, let's do another example. Example 4. And for all of these, we're just trying to determine whether it's going to converge absolutely or whether it's going to converge conditionally. So the sum from k equals 1 to infinity, negative 1 to the k plus 1 over the square root of k cubed. Again, and just as a general idea of something that's good to do, let's first check if this is going to converge absolutely, because in that case, it's going to also converge conditionally, and so we'll be able to get both with just proving one thing. So we're looking at the sum of the absolute value of this, so the negative 1 to the k plus 1 will go away, and we're left with 1 over k to the 3 halves. Well, nicely for us, this is another p series with now my p as 3 halves. Because my p is going to be 3 halves in this case, I do know that this is going to converge. So this converges. And so my series here converges absolutely and conditionally. And conditionally. Great, so this allowed us to just check one different thing and get both absolute and conditional convergence. Okay, so let's go through one more quick example on this alternating series section. So example 5 is going to be the sum from k equals 1 to infinity of negative 1 to the k of k over k plus 1. Okay. So this is no longer going to be a p-series when we take our absolute values, so we can't just automatically use our p-series test in order to tell if this is going to converge or this is going to diverge. A good way to think about this, however, is I have a k over a k plus 1. As we get really, really big, what's going to happen is this k plus 1 is really going to behave a lot like a k here. And so my series is either summing up negative 1 to the k, which is the series that kind of bounces around or doesn't converge, or if we're looking at it absolutely, we know that it's going to just be the sum of 1, which certainly does not converge as well, right? We add up 1 a large number of times, it's going to be exactly that number. So in this case, we should probably expect to get that this series is neither going to converge absolutely or conditionally. Okay, so let's deal with converges absolutely first. So we are looking at the sum from k equals 1 to infinity of k over k plus 1. Now, if we do expect something is going to diverge, the divergence test is a great choice because it will always tell us if something diverges. So looking at the limit k goes to infinity of k over k plus 1, this is going to be a polynomial where the top degree of 1 is the same as the bottom degree of 1. So we can look at the leading coefficients as 1 over 1. And so this is going to be 1. Well, this is not 0, and so this is going to diverge by the divergence test. Diverge. Right, the divergence test says if this series, or if this limit is anything but 0, this series is going to diverge. Okay, what about the alternating series? K equals 1 to infinity, negative 1 to the k over k plus 1. Well, we can do the same thing in this case, right? If we take the limit of our AKs being k over k plus 1, and we take the limit of this, k over k plus 1, right, we're still going to get 1 here as our answer. And so the alternating series test is going to tell us that this is going to diverge in this case, right? Another way to think about this, and one that might be a bit more clear actually, is let's just do the divergence test on this sequence. So we're looking at the limit as k goes to infinity, negative 1 to the k over k plus 1. Now, for all of my even terms, k plus 1. I don't know why the book adds this plus 1 to the negative 1 right here. It doesn't really matter if you start adding or subtracting. It's just the convention the book takes. So if you run across a series where this is a k instead of a k plus 1, it's still an alternating series. It's just saying we're starting with subtraction instead of addition. Okay, anyway, if we look at this limit right here, for all of the odd terms, so odd terms, the negative 1 to the k plus 1 is going to go away, so these are going to converge to 1. But all of my even terms, where I still have this negative here, are going to converge to negative 1. And so what this is going to look like is something where we bounce around in my even and odd terms between getting closer to 1 and negative 1. And so we can see from this it's clearly not going to converge to any value because half the terms are really close to 1 and half the terms are really close to negative 1. So this limit here as k goes to infinity of negative 1 to the k plus 1, k over k plus 1 does not exist. Does not exist because we have this oscillating behavior between 1 and negative 1. So because the limit does not exist, this series from k equals 1 to infinity, k plus 1, k plus 1 is going to diverge by the divergence test. Right? The divergence test doesn't necessarily need the limit to be some number. As long as this limit is not equal to 0, the series is going to diverge. So in this case, because the limit does not exist, clearly does not exist means it's not equal to 0. We know that my entire series is going to diverge from the divergence test. So this is a series that doesn't converge in any sense of the term, right? It's not going to converge absolutely or conditionally. It's just going to